Let's go through the whole of AQA gravitational fields. We're going to start off with some basic definitions. First of all, gravity is a universal attractive force that acts between all of matter, also including photons, but that's a different story outside of A-level. Gravitational fields, and just fields in general, are a region in which a body would experience a non-contact force. The gravitational field lines show the direction of a force on a mass placed on a field. So what does that mean? If I placed my mass over here, the gravitational force will be along this line towards the mass. If I place it here, it will be along this line towards the mass. This is also the direction that a stationary mass placed in the field would initially move. It's really important to know that the strength of the field is represented by the density of the field lines if they're closer together. So for instance, let's say if I was to double the mass, then I would end up doubling the gravitational field lines. And now let's have a look at Newton's law of universal gravitation. Imagine that we have two objects. These could be any two objects made out of matter. Let's say that this one here has a mass m1 and this one here has a mass m2. Well, they're going to attract one another. The famous equation for the magnitude of that gravitational force is that it's proportional to the product of the two masses, and it's inversely proportional to the distance between them squared. There is a constant of proportionality there, which is known as G, the famous gravitational constant. Okay. The value of G is 6.67 multiplied by 10 to the power of negative 11. Well, what are the units of G? Shall we just work it out rather than write them in? So if we were to just rearrange this equation for G, I'm just going to carry on across here. We're going to get that G is equal to FR squared, and then divide that by M1 and then M2. So this means that the units of G can be expressed as newtons meters squared, divide that by kilograms squared. So this here will be equal to N meters squared kg to the power of minus 2. A problem that can come up quite often, though, actually involves the SI base units of G, and I think these are also well worth deriving. So remember, the Newton is not actually a base unit. So we're going to need to convert the Newton into base units. So because force is equal to mass times acceleration, 1 Newton is actually equal to 1 kilogram multiplied by 1 meter per second squared. So this here will be equal to kilograms meters s to the power of minus 2. This was just the Newton multiplied by the rest of it, which is going to be m squared kg to the power of minus 2. So we can tidy this expression up to get the base unit, which is going to give me kg to a power of minus 1. This is just kilograms divided by kilograms squared, or kg times 10 to the power minus 2. Then meters and meters squared, that's going to give me meters cubed. And the only thing we have left is seconds to the power of minus 2. On to gravitational field strength. This is defined as the force per unit mass. Mathematically, we can actually say that G, which is our gravitational field strength, is equal to force per unit mass. Because the force is equal to gmm divided by r squared, this here is just the force. If we were to divide this by the mass, these are actually going to cancel. What we're left with is our equation, the G is equal to gm divided by r squared. In this case, m is the mass which is causing the gravitational field, and r is the distance from the center of mass to our position, essentially this distance here. Now, where does this equation actually come from? Imagine that we are on Earth, so now this is a different picture, and then we have an object which is falling down. Its distance all the way to the center of the Earth is r. Okay, so there's going to be a gravitational force which is acting on it, and the net force, or the sum of all forces, is just going to be equal to gmm over r squared. So this means that our net force is equal to mass times acceleration, which is equal to gmm over r squared. And notice how our masses are going to cancel out. This here is just the mass of the object that is falling, and capital M is, let's say, the mass of the Earth. Well, the acceleration is gm over r squared. Well, this is just another word for gravitational acceleration, g, which is just equal to gm over r squared, i.e. gravitational field strength. We can even calculate g on the surface of the Earth just using some values that are given in our formula booklet. We know that the mass of the Earth is, according to our formula booklet, approximately 5.97 multiplied by 10 to the power of 24, and our radius of the Earth is, 6.37 multiplied by 10 to the power of 6 meters, and that's in kilograms. Well, on the surface of the Earth, the radius of the Earth is going to be the distance. So we can calculate g to be gm over r squared, which is 6.67 multiplied by 10 to the negative 11 multiplied by the mass of the Earth, 5.97 times 10 to the power 24. Divide that by the distance, or the radius of the Earth squared, 6.37 multiplied by 10 to the power of 6 squared, and we're going to get approximately 9.81 meters per second squared. This is where this value actually comes from. Here is a little example problem that I have made up. Object X has a mass of m and radius r. Object Y has a mass 5m and radius 2r. What we need to do is find the ratio of the gravitational field strength on the surface of X over the gravitational field strength on the surface of Y. So in a way, we want to figure out this ratio of gx over gy. Now, my tip for ratio questions is to always write them out in terms of symbols, because lots is going to cancel. Okay, the gravitational field strength on X will be given by gm over r squared, and then the gravitational field strength on the surface of Y will be given by g 5m over 2r squared. Notice how I've put the brackets here because the 2 is also going to be squared. Now we can do some cancellations. So g is going to go, the mass is also going to go. We're also going to have a factor of r squared, which is going to go. So what are we actually left with? Well, we are going to have at the top, we're just going to have 1, and then at the bottom we're going to have 5 divided 2 squared, which is just a 4. So 1 over that is just going to give me 4 over 5. The distance between the center of two masses m and 5m is x meters. At position r, the gravitational field strength between them is 0. Find an expression for r in terms of x. Okay, so at this point right over here, in order for the gravitational field strength to be 0, if we were to place, I'm just going to draw it over here, a little mass, then that's going to experience a gravitational field strength or gravitational attraction towards this point, towards m, but will also experience exactly the same in the opposite direction towards 5m. At that particular point, they're going to be equal and opposite. Okay, so because they're going to be equal and opposite, we can say that gm over r squared, this is the gravitational field strength due to mass m, is going to have to be equal to g 5m over the distance from this center to r, which is just going to be equal to x minus r squared. Okay, so what we can do then is do a little bit of cancellation. So g is going to cancel, m is also going to cancel. Then what do we have left? We have 1 over r squared is going to be equal to 5 over x minus r squared. Let's do a little bit of cross multiplication. So I'm going to go 5r squared is equal to x minus r squared. Now we can probably square root everything. So we're going to get root 5r will be equal to x minus r. Let's bring all the factors in terms of r on one side. So we're going to get root 5r and then plus r is equal to x. This means that r, 1 plus root 5 is equal to x. 1 plus root 5, we can just plug this into a calculator, which is around 3.24. So we get r multiplied by 3.24 is equal to x. We're looking for r in terms of x, so r is going to be x over 3.24. r is going to be equal to 0.31 x. The gravitational potential has a very important definition. It is defined as the work done in bringing a unit mass from infinity to a point. The formula for the gravitational potential is given in our formula booklet, and this is just minus gm over r squared. It can also be defined in terms of potential energy. The potential energy a 1 kg mass would have at that point, and we can say that the work done to move something in a gravitational field is going to be given by delta W will be equal to m multiplied by the change in gravitational potential. There is another formula which is particularly important for graphs, and that is that gravitational field strength is equal to the rate of change of gravitational potential with respect to distance. The gravitational potential is defined to be 0 at infinity. Now, why is that? In order to really make sense of this, I'm going to have to explain something which is actually not on the specification, but it's pretty much the only way to understand this. So if you're not doing A-level maths, or if you want to learn exactly what's on the specification, feel free to skip the next few minutes. Okay, So imagine that I'm moving from point 1 to point 2 in a gravitational field. The work done is not just force multiplied by distance, because now the force depends on distance. The real expression for the work done is that is actually equal to the integral of the force with respect to distance. So between 2 points, let's say that the limits of integration are 2 and 1. So this here will then be equal to the integral of gmm over r squared dr, and gm and m are just constants, so this here is just the integral of r to the negative 2 over 1. Okay, so this here will then be equal to minus gmm, and then r, the integral of r to the minus 2 is minus 1 over r, so this here is going to be that. Okay, now this has to be evaluated at 2 points, let's say at r2 and then r1. So this here is, let's say, position 1, this here is position 2, which is then going to be equal to minus gmm over r2, then minus gmm over r1. Okay, so the work done will be equal to the sum of these two expressions. However, if we were to take one of those points to be infinity, as in the definition of the gravitational potential, then the limit of this function as r1 essentially tends to infinity, this function will then vanish because it's going to start tending towards 0, and then the work done, the gravitational potential energy, will just be equal to minus gmm over our final position r2. We can even just call it generally r. And that's one reason why the gravitational potential is negative, and that's why we define it to be 0 at infinity for pure ease of integration. Once again, this was not on the specification, but I get asked this a lot while I'm tutoring, so I think it's very helpful to make a video about it. Another important question is, does the gravitational potential increase or decrease with distance? Well, let's imagine that we have a certain planet, and let's say that on the surface of the planet, I'm just going to make up some numbers here, the gravitational potential is, 100 megajoules per kilogram. Then at some point later, it goes down to, let's say, negative 50 megajoules per kilogram, and then steadily goes to minus 10 and so on and so forth, and then it's 0 at infinity. So whenever we reach infinity, the gravitational potential reaches 0. Because it has gone from a very negative value to 0, it is actually increased with distance. And this is really, really important. Kind of like if we have gone from minus 5 to 0, we need to have inputted 5. You can almost think of it as a bank account. If the bank balance is minus £5, in order to reach 0, we need to input £5. So the gravitational potential increases with distance. Another way to think about it is, if I was to drop a small mass m towards that planet, let's say from here, it's going to reach with a certain speed v. If I was to drop it from further away, it's going to reach the surface of the planet with a much higher speed, which is higher than v, and that's another physical way to think about the same phenomena. Now let's talk about a really important concept, and that is equipotential surfaces. So they're defined as following. The gravitational potential is constant along an equipotential surface. In the case of a planet or a point mass, the equipotential surface is actually going to be simply a circle. Let's see if I can just about draw it roughly. So notice that the distance towards the center is always the same for a circle. This is not the only equipotential surface. In fact, there will be infinitely many, and we can draw a few of them like so. If we wanted to, let's draw one more. So a couple of important points. The field lines are actually perpendicular to equipotentials, and this is something that comes up quite a lot. Notice that if we look at any point, we have radial lines which are perpendicular. So this angle here is 90 degrees, this angle here is 90 degrees, and this is a rule that we can use quite a lot in problems. The closer the lines are, the stronger the gravitational acceleration, the equipotential lines I mean, and then something which is really important, that no work is done when moving along an equipotential surface. So if we were to place a satellite along an equipotential surface, we don't have to keep inputting work to make the satellite go around in orbit. This is also illustrated by the equation that delta W is going to be equal to m delta v. So if the change in gravitational potential is equal to 0, then this here will also be equal to 0, the work done. Let's explore a little bit more this, that the closer the equipotential lines are, the stronger the gravitational acceleration. Well, imagine that I have a point mass across here. If I was to draw the equipotentials, initially they would be quite close together, because the field lines, because the gravitational field strength would be quite strong. But as I'm getting farther and farther away from it, the field lines would keep separating more and more. I know these are not perfectly lined up, but the reason why their separation increases is because the gravitational field strength drops rapidly, because gravitational field strength is proportional to the inverse of the square of the distance. And here's a really important problem on equipotentials. What we have here are lines of equipotentials near the surface of a moon. Which way is the gravitational field lines pointing at point 1? Now, one good strategy to have is to always start by thinking where infinity is. So remember, V, the gravitational potential, is 0 at infinity. Well, if we look at this diagram, if we go down, we are actually approaching infinity. So we go minus 100, minus 50, minus 10, somewhere far out in the distance at infinity, the gravitational potential tends towards 0. So infinity is somewhere along here. Now, on the other hand, the moon is going to be somewhere across here. So which way is the gravitational field line going to be pointing? Well, we know that it's going to be perpendicular to this surface, and the question is it going to be up or down? Well, gravitational field lines will always point towards the object, so in this case the answer has to be up, like so, with this here being at 90 degrees. Next one, what quantity is given by the area in the following graphs? So first we have a graph of force against distance. Well, no matter what type of force, be it gravitational, be it mechanical, or any other type of force, the area underneath the graph between 2 points will be given by the work done. In this particular case, it will be the work done to go from here to here in a gravitational field. So if we had a graph of G, the gravitational field strength, against distance r, then let's say between 2 points 1 and 2. The area will be given by the change in gravitational potential between the 2 points. A good way to think about it is that G is equal to minus delta V delta R, which is given in our formula booklet, meaning that delta V is given by G delta R in terms of its magnitude. So this here is going to be G times delta R and G times delta R. It's useful to remember that the area in this case is the changing gravitational potential. Another question which appears often is what quantity is given by the gradient of a graph of the gravitational potential against distance. Well, remember, G is equal to delta V over delta R, and if we really think about it, this is just delta Y over delta X, meaning that G is in this case the gradient. In other words, gravitational field strength is the gradient in a graph of gravitational potential against distance. And now let's start talking about the orbits of planets and satellites. Imagine that we have a satellite over here that is orbiting a planet. It's important that this orbit is stated to be circular. Well, one of the things that we can define, for instance, is the orbital period. It is typically given the symbol T, and it's simply the time that it takes for it to complete one full revolution around its orbit. There are at least two ways that we can work out the orbital speed of a satellite. One of them, let's call the orbital speed V, is simply distance divided by time. Why is that? Because we can assume that the satellite is moving at a constant velocity along its circular orbit. So shall we say that the radius of the orbit is r, meaning that the distance will be given by the circumference of the circle, which is just going to be 2 pi r divided by the time period, which is just capital T. So the orbital speed is simply 2 pi r divided by t. We can also find it using a different way. If we think about forces, well, there's only one force which is acting on the satellite, and that is the force due to gravity. So we can say that the gravitational force, I've just called it Fg, is equal to the net centripetal force. Why centripetal? Because it's moving in a circle. This is essentially just equal to ma. However, m is just v, a is just v squared over r. So, and our gravitational force was gmm over r squared is going to be equal to mv squared divided by r. Now we can do some cancellations. So we can do that. And we can rearrange for v and then square root everything to get that the orbital speed will be given by gm over r. Finally, we can also talk about the kinetic energy of a satellite. And this is just equal to, of course, a half mv squared. Now, I suppose we could substitute either of those expressions into v to get two separate expressions for the kinetic energy. What typically comes up either in a multiple choice question or in a show question is using this expression. So I'm just going to say that this is equal to a half m. Now, this expression squared is just going to give me gm over r. And this is one way to express the kinetic energy of an orbiting satellite. There is a very important derivation that comes up a lot in physics exams, and that is showing that the square of the orbital time period is proportional to the cube of the orbital distance. So how do we start this derivation? The important thing is to remember that this derivation is all about forces. So take the gravitational force, I'm going to say Fg, and set that equal to the net centripetal force because this thing is moving in a circle. Okay, so we're going to get GMM, divide that by r squared is going to be equal to, now for the centripetal force, I'm actually going to use m omega squared multiplied by r. This is a formula given in your formula sheet and it will just make things a little bit easier. I'll show you a different way to do this in a second. And then just remember that omega is just 2 pi over the time period. Okay, let's tidy this expression up a little bit so we can cancel out the m's. And then we can also bring this r over onto the other side to get gm over r cubed is equal to omega squared, which is 4 pi squared. Don't forget that we need to square the pi as well. That's a very common mistake. Divide that by t squared. And we're essentially done. All we need to do is just do a little bit of rearranging. I'm going to do a little bit of cross multiplication. So this times that. So we're going to get t squared gm is equal to 4 pi squared r cubed. Final bit of rearranging, t squared is equal to 4 pi squared over gm r cubed, and we have successfully shown this. You can also do this by setting gmm over r squared to be equal to just mv squared over r. Then how do we put the time period in if we use this equation? The two methods are really equivalent, just a different way of arriving at the same thing. Well, v is just equal to 2 pi r divided by t. Okay, well, let's tidy this up a little bit. So I'm going to go this here is going to cancel. So I'm going to get gm over r is equal to v squared. Now, v squared is just equal to 4 pi squared r squared divided by t squared. And now we can just do a little bit of rearranging again. So we get t squared gm is equal to 4 pi squared r cubed. In other words, t squared is equal to 4 pi squared over gm r cubed. And we have shown this yet again. And here's a really tricky concept, and that is the total energy of an orbiting satellite. So if this satellite is in orbit, its total energy, so let's see, what should we call this? I'm going to say E total is going to be equal to the sum of its kinetic energy plus its gravitational potential energy. Okay, so E total will then be equal to a half mv squared plus the potential energy. Now, the potential energy, remember, is equal to distance multiplied by the change of gravitational potential. So a very useful expression to remember is that I'm going to write it actually on the side in a different color, is that E subscript P, or gravitational potential energy, is equal to minus GMM over R. Now, if you're doing AQA in particular, this is not given in the formula booklet, but please remember it. It's very, very useful. Okay, so this will actually change our expression a little bit. So we can get rid of this plus sign, and then what we're going to get for the total energy is a half mv squared minus GMM over R. Okay, so this here is the kinetic energy, and this here is the potential energy. So if the total energy of the satellite is 0, then the satellite will be free of the gravitational field. It's almost a bit like the ionization energy of an electron. The energy is defined to be negative in orbit. If the satellite is in orbit, its energy is negative. Please note that very often we have to plug in the value for the orbital speed using one of the expressions we looked at previously to get the expression for the kinetic energy, and then potentially work out the total energy of the satellite. If the satellite has reached its escape velocity, its total energy is actually 0 or even positive. So this here is the threshold. So 0 will be equal to a half mv squared minus gmm over r. So I'm going to put a little note here that this is for escape velocity. Well, that means that gmm over r is equal to a half mv squared. We can do our usual bits of cancellations. I'm going to rearrange it here that v will be the square root of, 2gm over r. And this here is an expression for the escape velocity of a satellite. If the satellite, or whatever it is, it could be a rocket or a spaceship or something like this, is above that actual value, it will escape from the surface of whatever is being orbited. Another important question to answer is, why do we actually launch satellites from near the equator and not the poles? Well, the answer is within this equation. Imagine that we have the Earth. Let's draw the Earth across here. Let's do a slightly better job. That's a bit better. Now, the Earth is spinning around its own axis. In real life, it's a little bit tilted, but if we are on the equator, we are going to have a much greater rotational speed even before we start. Why is that? Because we're at a distance r from the center of axis. And remember, v is equal to omega r. If we're right at the pole, we're not actually rotating around the axis because r is equal to 0. So at the poles, v will be equal to omega times 0, which is going to be equal to 0. At the equator, right over here, v is going to be equal to omega times the radius of the Earth, which gives a sizable advantage. And this is why we always launch the satellites from near the equator. At the poles, the total energy is just going to be equal to minus gmm over r, so we're going to need to input a lot more energy to reach the 0. So this is at the poles. The total energy will be a half mv squared, which is going to be omega, multiplied by the radius of the Earth squared, take away gmm over r. So we're going to need to expend less energy to launch a rocket from near the equator. And let's also have a look at synchronous orbits. So the most famous example of this is a geostationary orbit, when we have a synchronous orbit with respect to the rotation of the Earth. So imagine that if we have a planet, so let's say this here is the Earth, and then if we have a satellite which is orbiting around the planet, let's draw it a little bit further out, then imagine the satellite is kind of like coming out of the screen a little bit like this in a circular orbit. In order for the satellite to be in a geostationary orbit, the following conditions must be met. Its time period must be exactly equal to 24 hours. So notice that this is the rotational period of the Earth around its own axis. It needs to be an equatorial orbit. In other words, it needs to be aligned with the equator, and it needs to move into the same direction as the Earth does, which is west to east. If all of those conditions are met, the geostationary satellite will always appear at the same point in the sky for an observer on Earth. There are several uses. If that appears, typically it's a one marker or as part of a longer question, for instance, communication, reconnaissance, communication. You can also say GPS, for instance, just to name a few. How can we figure out the height of a synchronous orbit? Well, let's say that the height of, or the distance towards the center of mass is r, and what we want to do is determine the height of the orbit above the surface h. In order to do that, we're going to use the equation that we derived earlier, that t squared was proportional to r cubed, and in fact it was equal to 4 pi squared divided by gm. So for the Earth, we know the value of the mass of the Earth is given in the formula booklet. We know what G is. We know that the time period is 24 hours. So we can directly rearrange for r cubed, which is going to be equal to t squared multiplied by gm divided by 4 pi squared. There's quite a lot of places where we can potentially go wrong with this. So I'm going to input the numbers really carefully. We're going to say that r will be given by the third root of the following. So let's just write it out as t squared gm over 4 pi squared first, and then we're going to input the numbers. The cube root, remember not to square root in this case. So for the time period, I'm going to put 24 multiplied by 60 times 60, because it's 24 hours, each of them has 60 minutes, each of them has 60 seconds. And then I'm not going to forget to square that. Multiply this by g, which is 6.67 times 10 to the negative 11. And then we are going to multiply this by the mass of the Earth, which is 5.97 multiplied by 10 to the power of 24. And then we are going to divide all of this by 4 pi squared. We are going to get around 4.22 multiplied by 10 to the power of 7 meters. Now notice that this here is the distance r that we have actually found. So we've just calculated this distance, but what we're really after is the height h. So in order to do that, all we need to do is just take away the radius of the Earth, which is just this distance here. So the height h will be given by the distance r that we found, take away the radius of the Earth, which is given in our formula booklet. So we're going to get 4.22 times 10 to the power of 7. Take away 6.37 multiplied by 10 to the power of 6, giving us around 3.59 or so, around 3.6 multiplied by 10 to the power of 7 meters. So this is the height of a geostationary satellite above the surface of the Earth. In an exam question, you may be given a different planet. You may be given Mars or the Moon or any other value of m, which is going to correspond to a different time period, which is going to give us a different distance r, and so on and so forth. But the method is always exactly the same. Just a little note that sometimes you may see this type of graph, the logarithm of the time period against the logarithm of the distance. Now, why is this line actually a straight line through the origin? Well, remember that t squared was equal to 4 pi squared over gm multiplied by r cubed. This is just a constant. Okay. So let's take the log of both sides. So I'm going to go log of t squared is equal to the log. This could be done in terms of ln, for instance. This could easily be ln of t and ln of r. 4 pi squared over gm r cubed. I'm just going to put some brackets here to show me that this is the log of all of this. Okay, now I'm going to use the rule that the log of t squared is equal to twice the log of t, which is going to be equal to, now I'm going to separate the logs, and I'm going to say that this is equal to log of 4 pi squared over gm plus the log of r cubed. All I've used here is that the log of x times y is equal to log of x plus log of y. Okay, now 2 times log of t is going to be equal to, what I'm going to do is I'm going to bring this one on this side, and then I'm going to say that this is equal to 3 times log of r. What I've done over here is I've brought the 3 outside of the log using the rules of logarithms, plus the log of 4 pi squared over gm. Now, we can even do one more step if we wanted to, because we're going to get that log of t is going to be equal to 3/2 log of r plus the log of 4 pi squared over gm, and this here is divided by 2. So this here is going to be the value of our intercept. This here is not necessarily 0. I've just drawn this graph as a guideline that it will be a straight line. The gradient should be 3/2. And this also shows that the logarithm of the time period is directly proportional to the logarithm of the distance, the orbital distance. Okay guys, hopefully this video was really useful to you. What I've got over here are some practice questions on gravitational fields that will really help you, and that's precisely why you should click on this video right over here. Enjoy.